Welcome to SARATHSRI Skill Development Programs. The present session for discussion is practical applications of finite elements in industry. Before going to the discussion of the topic, just to discuss some of the challenges in the engineering industry. Industry is facing getting first time right quality. So there is a lot of rework due to quality issues. At the same time, increasing trends of global warming and carbon footprint level due to rework, as well as there is ineffective usage of resources. As the technology grows, new materials and processes are getting involved, so thereby complexity involves. So it is obvious to generate the right solutions, at the same time getting the good quality, at the same time proper solutions. As the industry progresses, there are many multiple industries are coming up. There is interaction between the industries, at the same time expectations from the clients are high due to get to the rapid product development, hence to reduce the cycle time. To achieve all these things, at least the some of the skills are essentially needed, and how to address these challenges is at least I give some of the thoughts to how we can approach to address these challenges. To do that, knowing the product design stage to manufacturing stage, know how and why. If we know that, obviously we know how to uh, control and how to design or how to manufacture. So for that, how to get first time right. At the same time, attitude of getting first time right is essential. As the industry progressed for last 2000 years, there are a lot of past experiences, best practices, those are to be involved, those are to be used effectively. So going forward, as the present era is computer and its internet has to be used to the maximum extent to get the first time right or a good solutions in the many industries. To do that, extensive use of knowledge is required, skills are required, and engineers with skill uh, uh, resources are required. This can be done by proper uh, education and training and skill development. So one of the such skill is essentially is finite element methods and analysis. Before going into the actual finite element usage, development and application, just to cover the what is the background of these finite elements, from where it has come, how it has progressed so far. In the olden days, that mathematical forms or physical uh, concepts has to be formulated into mathematical problem that can be solved using the closed form equations, either textbook approach or some of the standard formulations. So using these formulations, exactly some of the methods has been standardized um, into particular a group of problems. So that's why any kind of problem can be categorized into some kind of a standard formulation, and that can be solved using the exact methods or closed form solutions. So to take some of the typical example in the olden days, like aircraft or some automobile, so the kind of calculations are involved is uh, very much involved. To do that, at least by performing the hand calculations or closed form solutions, It takes n number of days together to compute a particular resolution. But as a present day, that scenario is changed, and the uses of the computers, you can use the maximum extent. In the olden days, for example, to perform the some of the spar analysis, so to do the free body diagram, extracting the forces from the mathematical modeling, and from there you have to do all the force plots, and from there your calculations and all to be done on the paper by manually. So this takes a lot of time, and at the same time it is a prone to some kind of error that depends upon the skill of the engineer. So as that discussed, so this engineering solutions or analysis for a given mathematical challenge or mathematical problem can be classified into two kind of approaches. One is the exact method, and the classical method, and numerical methods. Whereas exact methods uh, is involve fundamentally governing equations using the mathematics by exact some of the problems, some kind of hand calculations, or using the standard equations. But whereas the numerical methods as a fundamental governing equations, they are typically approximate, and they are solved by many simultaneous equations or iterative steps. But in case of numerical methods, where the differential equations can be formulated into simultaneous equations by using this either finite element or finite difference approach. Some of the examples are the finite element Nastran modeling package, where it gets this solution can be done. So this engineering analysis in a broad way, it can be designed into classical methods and numerical methods. Whatever the present discussion, finite element comes under numerical method, where the entire structure is can be decomposed into small elements that represents the entire structure more or less. So that can be grouped to formulate into global problem. From there we can solve whatever required as the field variables. So in a nutshell, the finite element method or analysis is having a it can be applicable for the redundant problems, or as well as non-redundant problems. But mostly, if you apply for redundant problems where the degree of unknowns are more, by solving with the finite element method, we can get easily and fast with your present computer age. This finite element analysis, yes, there are two types. One is static analysis, one is dynamic analysis. If you apply for different kind of approaches, where linear static, nonlinear static, where this dynamic analysis model, frequency analysis, the applications involved from the starting from like aircraft, automobile industry, and like metal forming, and kind of crash or impact. There are many industries. This finite element analysis is depending upon is getting used in many industries. Then from where it started, this finite element it started from kind of a 1940s. So now it is 2000. Still, it is there is a lot of research is happening, and from there it can be progressed into further advancement in coupled with software development. So one of the fundamental governing equation for this finite element method analysis is equal to stiffness equation, where stiffness is equal to force by displacement, or force is equal to stiffness into displacement. So based on this equation, this entire finite element approach is based upon. So once we know the stiffness, once we know the force, then we can easily calculate displacements. So from the displacement, we can go calculate the strains, and from strains, we can go to the stress using the constitutive material relationships. So that can be discussed in the following like slides. So some of the commercial programs starting with Nastan and the Abacus and ANSYS, Algar, and other commercial softwares, where exactly we can use finite maths for the different applications. There are different softwares. Each package is maybe specialized in a particular area, but all coupled together will get some kind of fundamental very good finite element database. Whereas conventional, we can go for strength of metals or maybe that textbook or some of the standard manuals. But whereas in case of finite element, there is a mainly it is based on matrix based analysis. That is like a force based method or stiffness based method. In case of a stiffness based method, the nodal displacements are unknown, and in the system of equations, whatever may be the equations that were developed, so that how that from the displacements we can calculate the stress we can discuss. So the basic equations of displacement method is derived from equilibrium nodal forces, compatibility of displacements, and force displacement relationship. So again, the fundamental equation is equal to force is equal to stiffness into displacement. So then how this equation will give maximum importance. Physically, that stiffness K matrix describes how force is transmitted through the element. In case of elastic problems, Maxwell states that stiffness matrix is symmetric. That means the symmetry max is where exactly above the diagonal terms and below the diagonal terms are is the same. So this is reasonable. So the how, because the pulling a rod in one of the spring distance will other whole fix gives the same force. The pulling end two will give the same force on other hand. So that is, I think this have influence on one and another hand. So how this then once we have discussed these finite elements, how these finite elements can be uh, used in the discretization of continuous system. A continuous structure may be divided into discrete grid points connected by elements. Each grid point has 6 independent degree of freedom. A degree of freedom is defined as an independent component of translation or rotation. As in the space, there are 6 degrees of freedom, 3 translations and 3 rotations. And based on that, it can be easily in case of a displacements or rotation, in case of a forces and moments. So this will have a lot of um, a role in the finite elements in the form of forces as well as the displacements. So this is nothing but like a translation in x direction, translation y, translation in z at the same rotation. So these are all the 6 degrees of freedom that at every node can be having, whether it is a in a three-dimensional or a two-dimensional or a one-dimensional. But anyway, that depends upon how we idealize, so that a particular degree of freedom will exist. So, for example, if you take a rod under axial load, this is like a one-dimensional problem. Even though in case of each node is having a 6 degree of freedom in the free space, but as that comes to the idealization of like a 1D element, that can be like constrained or maybe condensed to 1 degree of freedom, where exactly that kind of rod element is having only 1 degree of freedom in the x direction. So with that approach, it is easy to generate, to formulate how exactly it is one-dimensional element or two-dimensional element, and that number of degree of freedom also plays a role. So in case of UD, in case of a like a rod element, so where exactly the force is applied on the other hand, and you have on other hand another force is applied. So we have a influence of one end force in another other end and force on the first one. So that will give some kind of a stiffness matrix generation of exactly the stiffness matrix of the rod element can be used in calculation of the displacements or nodal variables at each end. So that the step-by-step procedure is just to satisfy the equilibrium, then relate strain to displacement. So once you have a strain, then you go for stresses. So then once we have a stresses, then easily you can get the forces from that relationship. So again, from forces to displacements. So these are all different kind of steps, but maybe the order may be different, but at least in a more or less, this is the um, like number of steps that is involved in the finite element analysis. In case of a like a torsion, so for whatever we have discussed is how exactly we can do under a uniform axial load and tension, where stiffness matrix is equal to AE by L into AE by L AE by L into. So this is where exactly you have, in case of a uniform rod under tension, you have the stiffness matrix AE by L into these coefficients. But in case of a uniform rod under torsion, so that stiffness matrix will be, in case of AE by L, it is replaced by GJ by L, because in the case of torsion, it is replaced by shear modulus, and in case of the moment of inertia, it is a polar moment of inertia, and the rest of the parameters represents the same. But in case of extension, there is a, um, you have displacements in x direction, but in case of torsion, you have rotations, so that will play a role. So that overview of the finite element, it can be seen as, first can take a continuous structure connected by a discrete element, then formulate the individual element stiffness matrix, then assemble the global element stiffness matrix. On top of that, you can, once the stiffness matrix is derived, then apply the boundary conditions and force to get the field variables calculations. Once the field variables is calculated, then get the displacements, then get the strains and stresses. So based on the material constitutive relationships, this is the, in a nutshell, this is the procedure, that is what is happening in the finite elements codes. So that can be, because as the redundancy goes up, these finite elements analysis will play a lot of role, because number of unknowns are more as compared to number of like equilibrium equations. So then this calculation will become cumbersome. Then at the time, using a finite elements as a one of the tool, we can easily calculate the required parameters which are useful for our interest. So once, as the discussed on the finite elements, so then what kind of elements that are available and that are used in the finite elements library? Some of the elements is starting from the 0 degree, 0 degree to 1D, 2D, and 3D. So there are starting from the 1D is like a truss element, beam element. In case of a 2D, plate element, shell element. In case of 3D, like a brick element or a tetra element. In case of a 0 degree, so where you can use as a, like a scalar elements like a mass, or like a point node elements connectivity. In case of a like a rigid element like a multi-point constraint or a rigid beam element, where to represents a heavy rigid structure in the like structures. So that can be used as a like like load transfer, or like between one node to other node. So that will be useful in our analysis. So having said that, this model, it once you given a geometry, how we can that bring to that to as like mesh shape. So based on the geometry, just to based on the our area of interest and the type of analysis, or our area of interest, we can assume that what kind of elements can be selected. So that then based on the rationalization and like idea generation, we can get the required element formulation. So from there, we can go ahead further building of this finite element mesh. So once the mesh is ready, check for the quality issues, so like what is the aspect ratio and Jacobian and skew angle and other parameters. So once that is done, so then you can go for selecting, assigning the properties and applying loads and boundary conditions. Then go for analysis whether it is a linear or non-linear. So this is whatever we have discussed. What is the meshing model, mesh type. So once this is done, so then just before going into further, just I wanted to cover a couple of case studies where, from the practical scenario, where from the where we can use the one dimensional element, two dimensional element, three dimensional element, and your rigid element, and like scalar elements like spring elements. So this shows the application of these elements in the practical scenario, and how it will solve and it will help for our engineering judgment or engineering analysis. In case of a first like a bridge analysis in the highway bridge, a typical highway bridge, how it can be done. So this is the typical highway road bridge. Some of the like a standard well-known bridge for any kind of bridge looks like it is selected over a river, um, like vertical pillars on top of this the deck, and there is a cables to give a support to this vertical column. So this is how we will analyze it, given the configuration, and how we can know that whether this bridge is having enough strength to withstand the given loads. So some of the idealization is like the 1D element, like a beam element and like a truss element, and with that boundary conditions, like where exactly it is erecting, easily it can be given boundary conditions, and the loads, how exactly the loads coming onto this deck, and there are different kind of loads that are coming. So some of the loads are there's like permanent load or transient load. Permanent loads include that inertia load, dead loads, and due to the filling material differential settlement loads, settlement and loads derived from nature of the structural material, like a creep and case. And in case of a transient load, like a wind loads, temperature loads, and erection loads, primary and secondary highway loading, footway and cycle track loadings, there are many kind of. So primary, among these primary highway loads are vertical live loads, where like a movement of vehicle or movement of like a pedestrian or like a vehicle load. Also, all these things comes under the primary. In case of a secondary highway load, there is like a change in the speed or direction of the like a centrifugal force when the vehicle is coming at a different like a curvature at like a speed. There is a centrifugal force, and if you apply a brake, it comes, it exerts pressure on the like this vertical this horizontal deck, that will create a kind of a force, like the skidding and collision forces and the seismic forces that are made. So here some of the analysis has been done to get the how exactly this simulation. But here, due to the vertical like a moving load in vertical direction, how this bridge will like a deflect, this we are going to see now. So this, as the load, moving load goes from here, see how that there is a pattern in the bridge, there is a pattern that this bridge deck. So as the load goes in the center, so this deflection pattern is also is giving more, actually it is so that's we can see that how exactly it is behaving. It's like displacements are like a vibration mode. So this picture is shown as an example how well loading load can play a role on the, so this deflection of the this deck. So there is another case study taken from the other aerospace and automotive industry. There is like a joint analysis. So in case of aerospace or automotive, there's common joint is like a power transmission between one power unit engine to that like a wheel in the form of a power transmission shaft. In case of helicopter, it is from the like engine to the tail drive shaft is through like a shafts only, drive shafts. So these drive shafts, it can't be that much long. So these has to be connected by segments that is joined by some kind of a triangular patchwork. So how exactly this patchwork can be used? These kind of three arm like three arm this is like a faced triangle faced like flanges, how exactly it is connected together, and how we will do the analysis and the kind of a force transmission and its design. So once we know this, how exactly whether to go for linear, non-linear analysis. So when we can use linear, when we can use, in case of linear, when the displacements are small, when there is no dynamic, and there is a elastic material, we can use this displacement. In the case of this elastic and linear and elastic analysis, there is only displacement on the stiffness matrix. This stiffness matrix can be formulated only once, and that can be used throughout the analysis. So in case of a nonlinear, where the displacements are high and where is like large displacements and nonlinear boundary conditions like contact elements. So at the time, this nonlinear analysis can be used, but how exactly you can get this nonlinear analysis? So this is in case of a nonlinear analysis, every load step increment, we need to invert the stiffness matrix and we need to update it. So that is where this entire crux is there, where exactly the stiffness matrix keeps on updating. So it will take a lot of time to do this nonlinear analysis. However, it will give exactly that actual behavior in the structure. So some of these packages are Nastran, LSDana, PamCrash, and ANSYS. So some of the nonlinear codes explicitly are available. So this is like explicit analysis where intermediately you can update the stiffness matrix. So you can see that some of the example whatever we have seen, that flange, you can see that flange segments can be joined together. This is like a section where exactly we have taken the three-dimensional analysis for the joint analysis. So it is joined by a bolt. It is connected by rigid beam elements, and these two flanges are joined by contact elements. And here the flanges are connected by again um, like kind of like a spring and RB2 element. And there is a flange here. There is a flange here. How exactly it can connect to each other? So that it can be shown here. So here there is a plate, here there is a overhead plate is so these two are connected by helic. So in some cases it is like over the plate you will connect another plate in case of a repair. If there is a like a shaft, if there is a plate, if there is a cutout late repair, so you can get a base plate like a doubler plate to do the repair. So that kind of so there are many things we can do using these finite elements. So what kind of loads we can, like a power loads, like a bolt preloads and axial load. So like here you have a from the in case of a power load, and because of that power load you will get it some kind of a torque tangential force. And in case of bolt preload extension you will get this kind of a load. In case of a axial pull on this one you will get some kind of a like a bending load at this a root of it can at this you can get a bending moment. And there are different kind of approaches you will use in this one in case of a, as it is a like a flanges because of this temperature effects. So to do that some of the elements used is 3D hexagonal elements and the shell elements, and like RB2 elements like scalar spring elements, gap elements. So many are used to represent the actual mathematical formulation of the physical problem. And based on that, giving appropriate boundary condition, as we have taken is a sector model. You can take a symmetry boundary conditions on either side, because in case of either most of the times if the symmetry like structure is symmetry, if the load is symmetry, then you can go for like a quarter sector model. But in case of some cases structure may be symmetry but load may not be symmetry, so at the time you have to use whether to go for symmetric model or like a full model. So that depends upon engineering judgment. So some of the analysis after putting this solution criteria and convergence. So there is some of the analysis, nonlinear analysis. Based on that, you will get a displacement plot. In the you will get a stress plot, and after that, as discussed, now how exactly the load flow can happen from the like a base plate to over the doubler plate if it is connected. Just a simulation has been done on the simple. You can see that how exactly. So you can see how exactly this is connected. So based on that you can see how you can easily connected. This is see how exactly the load is transferred here. So that the way if a load is applied, so it is transferred through this base this doubler plate over this is like where exactly in the central region it is more. That's why the patchwork is shown um, in the in this region it is more. So this is the reason whatever the band of that image it is showing, that is like a load flows from here to here again to go here. So this is like simulation. So this is in a nutshell a couple of case studies how exactly this finite element application is used. So now I will go for use of this getting this solution, or maybe in case of a design means design solution, in case of a manufacturing means manufacturing solution. How you can use this SARATHSRI concept to generate these solutions. But so far we have used while developing the solutions for in this case I have taken a design. So we have used the extensively on the finite element skills. We have used our ideas, we have used our thoughts, we have used a rational formulation. At the same time we have used the relevant elements like resources like softwares and other like time and money. At the same time engineers with the skills will become skilled engineers used this to solve the any kind of this design. But however when this if you group this into single like a framework, then we can get seriously how we can say to generate to a solution for a given challenge. So first we need to give a rationalization, we need to give a rationalization, idealization, and physical mathematical problem. Physically whatever it is there, just we need to formulate into mathematically rationalization. And at the same time you need to analysis that one, how exactly we can go further into our like a solution, whether it is in case of a design or in case of a manufacturing. So at the same time you have to use our ideas actually to use that what kind of formulation you have to use in case of a skill formulation. In case of a finite elements usage, we have to use whether you go for 1D or 2D. There is like a idea generation, and that depends upon the history of like experience and the theory. And you can generate the procedure from the thoughts itself. So these thoughts also we have to use extensively to get the proper solution process solution. uh, exactly the skills are used where exactly in this case finite elements, at the same time engineering domain. And in case of a design we can use, in case of a manufacturing also we can use manufacturing skills. At the same time to do that relevant elements to do this like resources like time and money, and you can use the process properly. And if you wanted to go for exactly the like other parameters like Six Sigma or like a 5S or maybe Kaizen, you can use that to define the process and the elements which are all relevant or required for your problem. And that can be fit into these relevant elements of this here. And once you apply all these things then on given the industry that design or like a manufacturing challenge, so then you will get the solutions. So finally you will get these solutions. So to get the solutions by applying your rationalization rational thoughts skills and relevant to the industries. So this is like a thoughts means with like a theory or thoughts with the history lack of knowledge, we can easily get this proper solution. That is nothing but SARATHSRI approach. So when SARATHSRI approach, there is always a good chance and get possibility to get a first time right. So if you use all these elements properly, judiciously. So this is in a nutshell SARATHSRI. But I believe in SARATHSRI because it is a it brings all framework, all individually whatever we are doing into a single framework. So that can give a focus on the these elements at the time of any like a project or a solution development process, in case of a design or a manufacturing or like a software and any other. So any everything whatever we do in the form of a development or a generation of like a solution, that that it can be that is fit into this SARATHSRI. So that's why this is like it can be used in any industry, not only in case of engineering or maybe non-engineering also it can be fit into that. This can be checked out here in case of for this problem, for this challenge whatever for this project, whatever we have developed this process for this finite element analysis. So you can this is a regular relevant process in this finite element. So what exactly it is this, we are pre-processing like developing the meshing and So then go for analysis, then again post processing. So this will form like one process in case of a finite elements. So this relevant process to finite element solution so will come as a relevant element here. So that's why whatever we do, we can define any process for our process like knowledge based engineering, or maybe like process individually, like uh, individual process like instructions or thoughts, like operating procedures. So that comes into this relevant elements to the industry. So once we fit into this and again use with this, so by focusing on this framework, this is there is a good chance of getting a like a first time right. So so once you having said this, then what is the general tips in this finite elements modeling? So use the like a proper like a meshing and proper inputs, and use the in case of otherwise it is a garbage in garbage out. So we have to give inputs properly, then we can simulate and simulate output as per the our inputs only, then we can take a proper engineering judgment. So whenever there is a whenever there is a uh, we need to do some kind of a cutout problem, so it has to be ensured that that mesh size around the cutout should be very much fine, whereas other regions it can be like reduced, it can be coarse. So in case of whenever the quick solution is needed for a nonlinear solution using the contact or large displacements or large deformation, so to get a first-hand information, you can then use the linear solution. So using the linear gap elements, so that can be linear gap elements that can save time and give a like a feel of information or a feel of solution, instead of going for like a lot of time consuming non-linear. So the same, whatever it has been discussed, when there is a cutout, we go for increased mesh size, increased density, like a mesh size is small and but the density is more. So as it's approach this in case of a like a crack, in case of a like a cutout, in case of a like a sharp corner, in case of a contact. So in that case, we have to go for fine mesh. But if you see here, in case of engineering structure or engineering professional, so when there is a like a smooth radius, you can see there is a there is no uh, there is no problem for this component. There is component is comfortable at the same time, and resting on this curved surface is comfortable, because here you have a like a greater section to take the load. But in case of a sharp corner, so where there is a very there is a possibility of getting crack, at the same time to relax of this human being, so he's feeling uncomfortable. There is no like a proper curved surface. So having said that, for this stress concentration, so but whatever we have done in the second example is a symmetry, and like approach how exactly use the symmetry. Once we have a loads symmetry and loads are symmetrical, geometry is symmetric, then go for even sector model, exactly represents the a quarter or half of that model to get the capture the results. So to do this stress concentration study, so where exactly you can see this, in case of a cutouts, you will have a large density, like when this mesh size is small, you can go large density. Whereas in case of other side, you have a like a biased, like in case of a coarse mesh. So this kind of approach we can use in case of a finite element analysis. But in case of this one, like a plate with cutout, we can see as an example, where there is a fine mesh, you can have a stress concentration more, whereas of coarse mesh there is no stress gradient. That is the difference between the stress concentration and other a region where there is no cutout. So so far we have discussed what is happening in the finite element industry from the past to the present. But now to touch upon the future trends, how exactly this future finite elements is going, what is its relevance. So in case of a future techniques, if you see that, so there is a for a future generation of the CAD geometry using the constructive solid geometry as well as boundary RIPA. So these two are all used for to generate the geometry But in case of construction solid geometry, you use a combination of basic standard shapes. But in case of a B-rep, you used as like create a solid with accurate surfaces. In case of future analysis routines, it will is coupled with like CFD, fluid structure interaction, coupled field analysis. So these are all the routines are can be combined and can like a robust finite elements. It can be applicable to many situations or challenges in the industry. Whereas in the case of boundary element, where exactly use the solid for 3D solid comments like linear heat transfer, linear 3D elasticity, fracture mechanics, integration of boundary element with the finite element will give a better result as well as periphery as well as inside the structure. And development of in case of a wing, in case of aircraft, the wing loads, there is a different kind of loads called bridge loads where there is a bending on the wing. Then you can have vertical compressive loads. But in case of this development of beam element, we can use really capture the loads that is uh, uh, taking on the upper chord or bottom chord or whichever maybe. So based on the idealization and the kind of requirement. So finally, in the future, integration of 3D CAD, FEM, and CFD and visualization can be single platform, so that that can use as like a powerful tool. In future, there is a similar to physical testing, there is a virtual testing also can happen, so that like a number of prototypes that is can be tested on the physical can be reduced. So far we have discussed on how exactly you will get like a geometry and how it mesh with the analysis results and the like a deformation and all. But now once you do, what is the guarantee that in the testing also you will get like a result at the same time? If you take the cutout, if you from the analysis you find out there is a cutout and you have stress concentration. But in case of physical testing or photoelastic testing, it is proved that even here also you get the same high stress concentration. That will give that our analysis predictions and the testings are give correlation. So this will give a go ahead scenario. So to prepare this simple session on the finite elements, I have used some of these references like a finite element methods and like a Wikipedia and some of the like a google.com like a website. So at the same time, universal framework SARATHSRI has been used to present in this session. It has been taken by www.sarathsri.com. So where it is gives some kind of like universal framework. So finally, just to cover whatever it has been discussed, it has been discussed on finite element history to present to future trend. And so far whatever we have done like individually, like concentrating skills or relevant or thoughts ideas just formed into single framework. SARATHSRI is an acronym which defines focuses on all developing solution which brings all six elements needed to get first time right, like solutions, application, rationalization, thought processes and skills and relevant elements to the industries. So once it gives us some kind of like a meaningful sentence. At the same time it gives like a, some kind of like a buzzword for the engineering analysis or engineering solution development process. So solutions are achieved by applying skills. In this case, is finite element analysis or synchrometrics, and at the same time, the process derived from thoughts. In this case, so the finite elements has been used. It means you can your ideas can be used to take which kind of element used, which kind of wide variation you need, and what kind of boundary conditions you can apply. That is almost like a rationalization and analysis approach. And so industry challenges like you have seen like a bridge design or like other joint design, so by engineers using right resources. But interestingly in SARATHSRI approach, so the relevant elements represents like which are all the relevant elements like resources, like time and money, and other parameters like individual standards and methods. So these resources will comprises of engineering skilled resources as well as other natural resources. But that SARATHSRI approach is used by resources, but that resources is also part of SARATHSRI. That is the beauty of this concept. So that it will give always talks about efficiency and high level like skills are required, and at the same time relevant elements means you can use that knowledge based engineering or maybe your optimum design or cost consciousness. So every parameters can be brought into it, the relevant elements, so then easily we can correlate it where exactly we are lacking, where exactly we are doing fine in a particular industry, or either in the software or manufacturing or like a design, or in case of academic or agriculture, any kind of industry. So this concept can be applicable. It is like another way of looking at things. So any other industry can get a first time right to any other day means like using the skills or maybe other individual like well defined process in their organization. But it is using the SARATHSRI is also one way of looking at that looking at that industry where you can focus on the elements and you can focus on the required elements which are all very specific to very varies industry to industry, so that once you have defined your required elements for your industry and you can focus on that how to optimize it and use it to the maximum extent. At the same time use the like the thought process and your rational approach to getting the better result. So in SARATHSRI technologies terms, it is the proper use and application of SARATHSRI. Thank you. So for more details on skills and solutions, approach contact at sarathsri.com and sarathsri.etechnologies@gmail.com. So thank you very much.